Hello everyone, we will start in a few seconds. Do you hear me? Thank you. The topic today is the IP layer part 2. A few more things in the IP layer that we didn't see, but that exist and that I call deviations. Those are deviations from the architecture in the sense that they're not clean things. They were not even designed at the beginning, but they came as needs by the industry, and we've seen some of them. The NATs are an example, but we'll see some more today. But before going there, a few words on the final exam. Given the status of the pandemic, the exam will be a take-home exam. The date is fixed. It will be on January 14th from 8:15 to 12:15. We will so a few indications about how it will happen. We will synchronize everyone in a Zoom session, but there will be no camera or no microphone needed for you. But this will give us a mechanism to keep in contact with you in case there is any question. We will also give a telephone number where we can call you, or you can call us, or send a text message if you want us to call you back in case the internet doesn't work, but telephone still does. The exam will be very similar to the previous year's exams, but the procedure will be different. You will need to download a text from our server and write your solution with your handwritten, with your hand. You can either write on paper, on white paper, take a picture or scan it and upload it to Moodle, or you can directly use a tablet, an iPad or a tablet PC of any kind that will produce a PDF or another format and upload it to Moodle. Of course, you will be at home, so you will need to comply with the honors code of EPFL that requires in particular that no communication of any kind with anyone is allowed during the exam. So you're supposed to do that alone. You're asked to do that alone. Of course, you can communicate with us, as we said, if there are any questions during the exam. It's open book. You can use every online or printed resource that you want, but of course, you cannot use that for communication. So you cannot use social media or post something and see the answer. In particular, you should not use anything that was made before the exam. In order to test your procedure, we ask that you do the mock exam. The mock exam is not meant to be an exact exam in terms of duration and difficulty. It's a really ridiculously small exam, but we ask you to write your solutions using the technology that you will use the day of the exam, upload it to Moodle, and then we will see whether everything works. That will allow you to test your equipment and your procedure, and that will allow also us to test whether what we receive from you is readable and satisfies with minimal things to help us grade, like, for example, put the number in front of the questions. Because the exam will be at home, we rely on you to obey by the rules, and in particular, there should be no cheating. We will try to detect any form of cheating. If we have any suspicion on the answers that you give, we will have several mechanisms to test this. If we have hints that you communicated with someone else during the exam, we are allowed, that's a special procedure this year, we are allowed to add an oral exam. So we can call you for an oral examination to examine whether you truly know what you are supposed to know. And this is allowed to confirm, which may mean decrease the grade if there is not enough evidence. If this or other procedure gives us evidence of cheating, that will be reported and sanctions will be applied. So please take this seriously. It's important for all those who work seriously that the exam has some value. In order to get prepared to the final exam, here are our recommendations. First, we ask you to do the mock exam, which has 2 steps, download and upload, and you must do that before submitting lab 6. Right, so please do that. It's very short. If your equipment works, it will be done in 15 minutes. but please do it now so that you have enough time and we have enough time to give and receive feedback. Now, to get prepared to the final exam, the best preparation is two parts. First, do again the quizzes in the course that are in the lecture notes and in Moodle, and take the two exams of the past 2 years. This year's exam will be very similar. It will be adapted to the fact that it's online, but it will be very similar in content. The major difference with respect to the exam of the past years is that the exam is open book. Open book means you can have access to all the slides, but also to all other documents, to Wikipedia or any other textbook that you can find online. But here a warning, don't count on it. It's a bad idea to think that because it's open book, you don't need to prepare and to learn anything. Go through the quizzes, do the past years, and when you prepare to the quiz and to the exam, try to do it by having only the exam booklet. The exam booklet is a small set of slides that we think you don't need to know by heart. The rest you should know by heart. If you don't do this, chances are you will simply be overwhelmed the day of the exam and you will not be able to work well, to obtain good grades. In the past, we had the exactly same exam that was done open book, and the grades were much less good than closed book, though the timings and the difficulty were exactly the same. And I attribute this to the lack of preparation of students because they thought it's open book, therefore I don't need to prepare for it. That's not true, so please take this seriously. Well, if there are more questions, please put them on the chat of Zoom or in the news group of Moodle, and during the break we might also discuss about the questions you may have. For now, let's move on to the content of this lecture. We'll start with something a bit weird called Proxy-ARP. Proxy-ARP is exactly an example of what happens when you violate the rules. Here is, for example, a rule. One of the rules of IP says that there should be identity between subnet, as seen by IP, and as implemented by the subnet prefix in all hosts, and the local area network. One subnet should be one LAN, possibly with bridges, but one local area network. Now assume that for some reason, we will see a few examples where this comes naturally, for some reason you want to cheat. Here I'm giving an example where I have a network where the network between two routers R1 and R2 has this prefix. And for some reason, I have connected to R3 a host that is on different ports than the ones that should be in this subnet and has an address that falls in this prefix here. Right. Of course, if you do this, you should take care of this by the routing table. For example, here at the routing table of R2, we see that if I have a destination that falls in the 12.12.12.0/24 prefix, we are on link. We should go to one of the interfaces that can be found out by looking at the table or other means. But if I go to this specific destination address, I should do something different. I should go to this interface here. So this is possible because IP has the principle of longest prefix match. And this is called here a host route. It's a route where the length of the prefix is the entire IP address here. So that will take care of the fact that R2 will send packets to this red thing to the correct destination. R3 should do something similar. So if you do this, of course, you should account for this in the routing table. But that doesn't solve all the problem. That's very typical. If you violate one rule somewhere, you will have a problem. And in order to fix the problem, you may need to violate another rule or more. So packets that are processed by those three routers will go the correct way thanks to the routing table. But assume now that the host A is on this subnetwork here and has a packet to send to this destination. Because A follows the rules of IP, it thinks that the destination is in the same subnet. Therefore, it will send an ARP packet to find the MAC address of the destination by sending a broadcast, if it's IPv4, on the local area network, asking for the MAC address of this. Of course, this will not work because the destination is not on link as it should be. So nobody will reply and the destination will be unreachable here. This, of course, doesn't work. A solution that is sometimes done is to ask that the host participate in the routing protocol using lightweight routing protocol like RIP that we will see next week and learns about this destination address. But this is done in some specific contexts where the hosts are industrial machines, for example, but this is typically not done otherwise because we don't want customers, people like you and me, to participate in the routing protocol of, for example, ePFL. So another solution is called Proxy-ARP or Proxy-NDP. ARP is when we use IPv4 and NDP is typically the terminology used when you use IPv6. The idea here is that, remember, the problem is A is sending an ARP request for this destination address, and the destination address will not reply. But one of the routers, for example, R2 here, could be configured to do it instead of the destination here. That is what we call a proxy. We've seen the concept of proxy for web proxy. A web proxy on the customer side is a web machine that pretends to be the final destination. Here it's an ARP proxy because it pretends to be the final destination. So if we configure R2 as an ARP proxy server for this machine, then it will reply to the ARP request. So when A sends an ARP request for the destination, R2 will reply. R2 will reply with its MAC address. And why is it a good idea? Well, because indeed, if A has a packet to send to this destination, it should send it first to R2. R2 is the first next hop. So R2 being pre-programmed in this way will do it. And we say that R2 is a proxy for ARP requests sent by anybody on this LAN. So this is something that is done in some configurations. For example, it's typically done in a VPN configuration. Assume here I have a machine here, like this VPN server that serves a machine here, and the VPN server has the property of giving you an IP address as if you would be at ePFL. For example, when I go to this machine over the internet via a VPN tunnel, I will get an address like this one here that is in the same subnet as the subnet where the VPN server is here. Now, what will happen when this machine ET0X has a packet to send to me on the VPN, but outside the VPFL physically here? What will happen? What do you think? I close in a few seconds. And the majority says A, which is the correct answer. So we have here a packet to send to somebody that's outside ePFL. Then the machines inside ePFL that are on the same subnet here will send an ARP request for the final destination. And obviously, somebody like this VPN server should reply to this request. So VPN servers typically must implement ARP proxy here. And that will take care of having the packets sent to Green MAC in this case. Voilà. So that is a first violation that we have seen, Proxy-ARP, which is often done. It has to be done typically by the routers, and it will hide to the end systems some violation of the subnetting principles of the internet. Here's another topic, which is a more nasty one, which is called fragmentation. Fragmentation is due to the fact that not all link layers have the same packet length. We could not agree on the internet of a maximum or a standard packet length. We know, of course, the standard one, which is Ethernet, or the most standard one, which is 1500 bytes. So this is the size called MTU, the size that is reserved for an IP packet, including the IP header. So that's the size available for the IP packet, including the IP header. So that's what an Ethernet frame gives to its payload. Right? But now there are many variants to that. Not all Ethernet frames give you 1500 bytes. Some give you more. For example, there are specific things called fiber channel that are special Ethernet, if you want. They don't work like Ethernet exactly. They work in a different mode of operation that are used for high throughput servers. If you have a server farm that is not used for web requests, for example, but for extremely high throughput requests like shuffling videos or doing entire database backups or recoveries, then there are other mechanisms that have larger packet sizes. This is also what is done, for example, in physics experiments at CERN, where you have huge amounts of data that are transferred from one place to the other. Then you use exotic Ethernets, if you want, that have larger packet sizes. Why do you use larger packet sizes? Well, because there is an overhead per packet. So the larger the packets, the less the overhead is here. There are other reasons, like, for example, if you are in a tunnel, which is the example I have here. If we look at my interfaces at home here, when I run IPv6 over my home network, I have a maximum packet size which is smaller, 1472. Why is it? Well, it is because, as we will see in a few more minutes, the IPv6 service that I receive at home is not a native IPv6, but is an IPv6 in IPv4. So there is some encapsulations or some other header translation systems that reduces the packet size here. If we go to the EPFL tunnel, we can see that in other interface here. If I activate from my home here the EPFL tunnel, I will see a much smaller packet size, and the reason is there are many layers of encryptions that are added here. And then you have more exotic things like ZigBee with encryption. Those are IP technologies that are used for Internet of Things if you want to connect small objects that have very low capacities, and you will have very small packet sizes. You have also the other extreme when you use the loop-back interface, that is when you communicate over IP inside the machine, then the maximum size is typically very large, for example, 4 gigabytes. So we have different packet sizes, and that causes sometimes problems. The problem is illustrated here. If I have a host on the left that has an MTU of 1500, so every machine, of course, can know what is its MTU, the packet size that's available locally, and will, of course, never generate a packet larger than this size. But there might be a network in between that has a larger size, a smaller size. This could happen typically, for example, when we have encapsulations or tunnels for virtual private networks that are not visible to the end system, but are visible, for example, to your ADSL modem here. In a case like this, there might be problems if this host generates a packet that is too large to fit here on the path between R1 and R2 here. So if that happens, we will need what is called IP fragmentation. IP fragmentations, in the example I gave, would occur at router R1. If this host sends a packet that is too large, and if the router supports fragmentation, it will fragment it. It may also happen at the source. Now you might wonder, why would you do that at the source? Because at the source, you know what is the size of your interface. What would you fragment here? And why would you generate a packet that is smaller? Well, there can be a reason for that. The historical reason is the UDP service typically mandates that the entity, the message that is passed is the entire packet. Remember, TCP offers a streaming service. When you receive data over TCP, you don't know where the limits are, where the boundaries are between data blocks. But with UDP, the service is guaranteeing you that we deliver exactly the blocks as they were put by the source. Then, if the source wants to send a block that is larger than the MTU, the host will fragment it into several IP packets. Now, for historical reasons, the fragmentation is done at the IP layer. So UDP will create an IP packet that is larger, and the IP layer will break it into smaller fragments. This is a bad idea. And today, the requirements are, if you create a new application today, you should not do that. You should have your UDP application worry about what's the maximum packet that works locally, but even end-to-end, and then find a way to create blocks that are not larger than that. But old applications, and many applications that exist today, don't do that. They relied on the fact that UDP in particular was not at all caring about it. Therefore, fragmentation could be done. So some of the rules about IP fragmentations is that fragmentation can be done at the source or at routers only for IPv4. So we see an evolution here in the internet. First, fragmentation could be done everywhere at the source and in routers. Then IPv6 came and said, oh, that's a bad idea. Do it only at the source. That was 20 years ago. And now, even today, the IETF says, no, never do fragmentation in principle. Of course, it's a bit late to say that, the existing applications will do it. So IPv6 routers never fragment. If they receive a packet that's too large, they will kill it, simply. Another element to remember is that reassembly, once you've split a packet into smaller packets, somehow you will need to reassemble it, and you reassemble it at the IP layer. It's not the sockets that will do it, it's the IP layer that will do it. And the reassembly is always at the final destination, never at intermediate points here. Last, all fragments are ordinary IP packets. This is in contrast to other networking technologies where when something is broken into smaller pieces, then we put some special header to the pieces to be able to recognize them. Here, it's all not the case. Of course, there are elements to recognize them, but every piece is a standalone IP packet. And if there are multiple paths in the internet, it's not impossible that the different fragments follow different paths. Some terminology that is, in this context, often used. If we need to make the difference between the big thing that was broken into pieces, then the big thing is called a datagram versus a packet. So a datagram can be split into several packets, every packet being a fragment. If there is no breaking, then one IP packet can contain an entire datagram. So we find that back to the original idea that UDP would provide a datagram transport service and would entirely rely on IP. Here is an example that illustrates how things are done. I'm showing here a packet of 1400 bytes plus 20, so 1420 bytes. And I'm assuming in the middle there is a path that has only 620 MTU. This is not very frequent, but that makes the example easier to explain. So at the source, if we examine things at the source, here, so at point 1, we will see, here I'm looking at the IP, the fields that we see in the IP header. We will see in the IP header, of course, the source and destination address, but we will see also fields that we have not discussed before that are called the length and the identification. The length is the length of the original date of the, not of the original, of the IP packet here, which is the payload plus the header. The identification is a number that is put by the source to glue together the different fragments. So every IP packet has an identification number, whether it's fragmented or not. But at this point here, at point 2, this packet, which is now too large to fit into the MTU of 620, will be broken into 3 packets. 3 packets with 620, including the header, plus whatever remains here. Now, if we look at each of those 3 packets. Remember, they are standalone packets, so they will have source and IP destination address unmodified. The length will be modified. It will be 620 for packets for 2A and 2B, and 220 for packet 2C here. The identification will be the same. That's the glue that helps them be kept together. And there is a bit, a flag that says whether it's the last or not. It's called the more bit. So if its value is 1, it means it's not the last. So the first 2 fragments will have the more bit equal to 1, and the last one will have the more bit equal to 0. This will help the reassembly at the destination. The destination hopefully will receive the 3 fragments. It may not receive them in order if there are multiple paths in the network and the routers don't do the kind of things we saw earlier in OSPF to keep the packets of the same flow together. Most will do, but if that is not done, the packets may arrive in any order. And when the packets arrive, then these different fields will be used to reconstruct by the IP layer the original datagram. It's used to reconstruct because, for example, if I receive the packet 2B before, I know that the packet size is 620, so I have 600 bytes of data here. Of course, in the packet, I forgot to mention, there is an offset that will say where in the original datagram the packet was. Here it's 600, so I will start reconstructing the payload starting at offset 600. And there is a more bit, which means it is not the last one. And assume after that I receive the fragment A, the offset is 0, so I will reconstruct the first part of the original datagram. And hopefully sooner or later I'll receive the fragment C, which will have an offset of 1200 and the more bit equal to 0. So I can test whether I have the complete packet by seeing whether I have at least one fragment with more bit equal to 0, and whether all the gaps given by the offsets and the packet length that I've received are there, whether there is no gap. So this is how reassembly will be done. As a small optimization in the number of bits, the offset is not written in bytes, but in words of 8 bytes, which allows us to save 3 bits in the IP header. But that's a small detail here. So this is how fragmentation works. Now, a quick poll. Assume we use TCP. One TCP segment is contained in one IPv4 datagram, but it's too large. Like, assume the example before, it was used by TCP here. And assume one of the fragments is lost. What will TCP retransmit? I close the poll in a few seconds. And the correct answer is the majority choice, which is answer B. If one of the fragments is lost, because reassembly is done at the IP layer, the IP layer will start reassembling, wait for some time, then will time out and will discard the partial fragments, and the entire packet will be deemed never received by TCP here. So this is largely inefficient. It's a bug in the design of the internet. We should not allow fragmentation at the IP layer. If TCP wants to fragment, then TCP should take care of it, but TCP has sequence number for every byte, so there will be no problem. And if UDP wants to fragment, then UDP should take care of it, or the application that uses UDP should take care of it. This is what we say today, but this is not what was said at the beginning of the internet. And of course, this is largely inefficient. In particular, because here, if you lose one packet, you see that you will retransmit 3. So if the network in the middle is congested, then we see that we amplify the congestion, because this network is signaling congestion by dropping 1 out of 3, but you translate that by a loss of 3 and a repetition of 3. So you compound the congestion. In fact, you remember in the mid-80s, there was a big congestion collapse in the internet that was due to the absence of congestion control. It was compounded by this effect that there was a lot of fragmentation occurring as well. Now, another question. When a host generates UDP traffic, is it true that the port number is always present in all packets? What do you think? I close the poll in a few seconds. I share the results, but I'm sorry to say the majority vote is incorrect, because if fragmentation occurs, only the first fragment contains the port number, because remember, fragmentation is done at the IP layer. So if I go back a few slides here, here, the 600 bytes that are shown here, that's the beginning of the UDP packet. The second part of the UDP packet is the middle of the payload of the UDP packet. So there will be, no UDP header, which is typically in the first fragment. So which means that if we do fragmentation, we don't have a port number in all packets, which is yet another problem for whom? For the NATs, of course, because the NATs rely on the port numbers to know what to do. So some NATs simply don't support fragmentation. So if the host fragments, then the packet will simply be discarded by the NAT. And with some NATs, there will be problems, which is again an illustration of what happens when you violate the architecture, whatever the architecture. I mean, fragmentation is part of the architecture. It's a bad idea, but it's part of the architecture. The NAT is an afterthought. That's a hack. And if you start using a hack, then there are things that don't work well together. That's an example. Now, if you buy a NAT from your provider, or if you receive it from your provider, of course, it will take care of that. So what NATs do today is, first, they will assume that the fragments arrive in the correct order, so that the first fragment is always seen first, which is probably true for your local area network at home. And when a NAT sees a first fragment, it must not only remember the IP address and the port number, but the identification number. So when a subsequent fragment arrives, the port number is lost, but the identification and IP addresses that are contained in the IP header can be used to recover the port number. So that is one more of the little tricks that a NAT must do. But this is still a problem for security, because you have many systems that check what is in the packets by doing deep packet inspection, for example, of the beginning of the packet. They read not only the ports and the headers, but they may start reading the beginning of the packet. So an attack, a documented attack on the internet, consists in fragmenting a packet, sending a first fragment that has completely correct values that are okay and that are accepted by all firewalls and intrusion detection systems, even those that do deep packet inspection. And then in the second fragment, send a fragment that overlaps or even if it doesn't overlap, then contains bad things. And then typically the firewalls will use the cached rules that are done here. So that can be used also by attacks. All of this means that fragmentation today should be avoided. How can we avoid fragmentation? Well, there are different methods that have been proposed. The only one that works today is this one, packetization layer path MTU discovery, a horrible acronym. The first idea that was used was to use ICMP. Remember, if a packet is too large and a router doesn't want to fragment it, which many routers will do, it would or could typically send an error message, just like when a packet has destination unreachable. And one method that can be used in an enterprise network is to, whenever the source receives an error message that the packet is too big, then it can infer that the MTU was too large. But that doesn't work typically on the internet, because routers in the internet don't like to do this because it can be used for attacks. So one stupid but simple method is to use the default MTU. That works well for IPv6. IPv6 says any implementation of a network component should always use that minimum size, which is large enough to be good for everyone. So you can avoid the problem at all by, in your socket layer, say, I generate IPv6 packets that are always never more than this size, and then it will never be too large for any packets in the world. If you use IPv4, then you may have problems because the minimum MTU for IPv4 is ridiculously small. And we've seen that some ZigBee systems, for example, use that type of things. But in practice, it's very special. And most systems should have a larger size, which you can use as a default. If you have this size here, it's probably because you are on a ZigBee system and you can probably test this locally. You don't expect that a link in the internet would have such a small size. So that's one thing that is often done, but for IPv4 it's very suboptimal. So one method that is used by Windows and Mac OS and Linux is to implement what is called packetization layer path MTU discovery, which consists in getting hints from the higher layers, the application layer, of what worked. For example, if TCP sends a packet of a given size and it was acknowledged, then we know that this size of packet is lower than the path MTU, lower than or equal to the path MTU. Similarly, if I have a UDP application, for example, for DNS, that send a DNS request and I receive a DNS reply, if my DNS request is formed such that it's very large, for example, but if I get a reply for it, I know that the packet I created was not too large. So modern operating systems monitor all of this in the operating system and use what is called a correspondence table, where we keep a list of all IP remote systems, and for every remote IP address, we keep a cache of all the MTUs that worked in the recent past here. And from time to time, you may want to start to try a larger value, and if it works, then you may stay with this larger value. Of course, there are other heuristics you can use. For example, if you know that the destination is on link, which you can infer by your subnet prefix, if there is no other hack, like we saw with Proxy-ARP a few minutes ago, then in those cases, you can infer that the path MTU is equal to your interface MTU, because the destination and you are in the same technology here. In the case of TCP, this is typically done at connection opening. When we open a TCP connection, one option that is always present is the MSS. The MSS is the size of the packet usable for TCP payload. So it is equal to, it's equal to the MTU minus the IP header minus the TCP header size. So a TCP implementation should always negotiate in the same packet an MSS that satisfies this constraint, while the path MTU is obtained by this interface MTU. And if there is no data in the interface MTU, we revert to the default. So this is what applications should do today in the internet, and in a few years in the future, when all applications do it, we will never have IP fragmentation. Voilà, that was the second ugly thing. Now, the third ugly thing of the day is called a tunnel. What is a tunnel? We encounter this word very often. So tunnel is a synonym for encapsulation. It occurs whenever we carry in the payload something that is not supposed to be there, typically because it's from a lower lane. For example, if you carry an IP packet in a UDP packet, then it's an encapsulation, or IP in TCP, or things like PPP, which is the layer 2, the equivalent of Ethernet on point-to-point links in UDP, or, as we will see, will happen frequently, IPv4 and IPv6, or IPv6 and IPv4. Of course, those are violations where the principles of the layered model is that inside the IP packet, you should have a UDP or TCP or ICMP packet, but not another IP packet, or not an IP packet should not be in UDP. However, there are lots of reasons for this to work. The most important ones today are the private networks and the IPv6, v4 interworking. Private networks, well, what's the story? For example, many companies have, including EPFL for the internal addresses of PFL, use the private addresses from a private block here. Now, assume you have several sites and you use private addresses of the 10.1 and 10.2 blocks. That's perfectly legitimate. But now, if you connect your sites with an internet service provider, a public provider here, of course, you cannot, without any further manipulation, simply communicate. You could put a big NAT here, but assume you don't want to do this because you really want those addresses to remain private. You would like that the different hosts on the left and the right work together, but as part of a private network without being exposed to the public here. Then what is done here will be a virtual private network and a tunnel. So, for example, we can simply use an IP in IP tunnel. An IP in IP tunnel means at a router here, like A, I configure an IP address B here. Those are public IP addresses here. And all the traffic that goes from, for example, from X to S here will be put inside this IP tunnel here. So the packets are carried as payload inside the IP tunnel. This is called IP in IP tunnel. And this is this is what is done in this example here. So assume S, which is here, sends a UDP packet to X. For example, this is a sensor in an industrial network that uses this tunneling technology to connect to a server that receives the result of a measurement here. If we do a Wireshark at this point here, what IP destination address will we see? I close the poll in a few seconds. And the majority says A. Again, I'm sorry to contradict the majority. It's true for the IP destination address, but not for the protocol type. If I do a Wireshark, I will see an IP packet that contains an IP packet. So the protocol type will be the code for IPv4, if it's an IPv4 packet. So there is a protocol type for IP inside IP, and the only explanations is this one. It is when we do tunnels here. And for IPv4, the protocol type is 04. So this is very often done, but with one added thing, which is security. Of course, when you exchange data of your private network over the public internet, you would not like anybody to be able to read the content of your data. So what is typically done is to add a number of layers. Security. Another problem here is, which is not a good reason, but a practical one, is that IP and IP packets are often killed by many firewalls. So if you do this, for example, for you at home, when you want to access the internet VPFL, then you would probably not be able to receive the packets unless you program your modem to accept this. So for this reason, it is often done inside UDP. So we will have an IP packet that contains a UDP packet, and the UDP packet itself contains an IP packet with additional information, because here we've lost, in UDP, there is not a protocol type. UDP does not have a field to say that what comes next is an IP packet, for example. So we add another layer. It's called, for example, L2TP-PPP. PPP is a layer that is used to, when you have a point-to-point link, for example, over your ADSL modem, to put information such as this one. What is the nature of the packet being here? Information that is otherwise in the Ethernet header. So this is one typical thing that will be done, so that costs a few more bits and will reduce, of course, the MT. As I mentioned, of course, you will tend to do this, plus to encrypt the packet. So there are two mechanisms that are typically used in VPNs. The first one is IP layer encryption. It's called IPSEC. IPSEC is allows to encrypt packets over an IP at the IP layer, but it requires an association. So here you would need to configure A and B to make what we call an associations between A and B, where they will agree on the encryption mechanisms and on the keys to be used here. Then there will be a header to help the decryption, and a trailer. This is very typical of all kinds of encryption. You need the header to perform the decryption, and the trailer to verify that the decryption worked well, that there was no problem here. And the inner packet is now completely encrypted. So the packet that was generated by X, the blue packet here, which is an IP packet with a destination 10.22, so there is an IP header here, but now it's completely encrypted. So this is one of the two mechanisms that is widespread. And of course, an attacker that tries to seed in the public internet what Simscom company is doing will not gain much information. It will get the information that there is traffic from A to B, but this is information that is probably not giving you a lot. You can still measure the volume of traffic, but you will not see not even the IP source or destination addresses of who is communicated with whom. So this form of tunneling is called an IPSEC tunnel. There's an alternative, which is also often used, which is called OpenVPN. That's the one we find in Linux systems, for example. It replaces this IPSEC tunnel with a TCP and TLS connection. So A will establish a TCP connection to B and a TLS association, very much like we did in Lab 3, but in Lab 3 it was to exchange application layer data. Here it will be to put IP packets inside the data here. So the OpenVPN tunnels use this technology. There are differences between the two, of course. When we use here L2TP IPSEC VPN, there is no congestion control done between A and B. Congestion control is done by X, but not by A and B. In contrast, when we use IP and TLS over TCP, the bitrate that's available for the tunnel will be congestion control. A will have to do all the TCP stuff. So if there is congestion in Simscom network, A will decrease the window size, so we have a tunnel of variable capacity. If we use the first form, this will happen only indirectly, and we trust that X and S, for example, are doing correctly congestion control, but the way they compete in the internet are different. Here there is one single TCP connection for the entire traffic, whereas here there would be many, many TCP connections. So there are differences from the bandwidth sharing viewpoint between those two solutions. I will conclude this first half of the lecture with this question. Assume we use here when we connect to VPN, to EPFL VPN, I am at A, I obtain this address here, the address, if I do an if config on my machine, I will see that I have obtained the address 8322. But my real address, of course, at home is a private address of my home network here. Now, when B has a packet to send to A, how does the packet from B to A finds its way? I close the poll in a few seconds. And the majority says A, which is now the correct answer. When the packet is sent by B, by the normal routing, it will reach R. R also, by the normal configuration of its routing table, will send it on this interface here, but will do an ARP request for this address, the 22, which of course does not exist here, is only on the other side of the VPN router. So we must have the VPN router do Proxy-ARP. So it's the VPN router that will reply with its own MAC address, and then R will send to the VPN router. Of course, now the VPN router knows that this destination address is on this VPN tunnel and will send it over the VPN tunnel. Voila, that's all for now. We break for a few minutes and we resume at 1:15.